and Yau. The original work we did was actually started in 2018. So, but the final version of this work appeared in journal in 2020. So it's pretty actually recent. And the reason I chose this topic is because there's also more progress we're having in this direction. So I can tell you a little bit about it.
So which Yau is this?
This is Shinkan Yau.
Same Yau.
Yeah.
Big Yau. Just Calabi Yau.
ST Yau.
Okay.
I think somehow all of them are big. So, anyway, so let me start my talk with some of the ingredients we use in our construction. So I want to talk a lot about Atiyah classes. So, yeah, class. So let's just start by setting some geometry. Let X be a given smooth projective variety. I work over C often. So I would like to say a little bit about the Atiyah class. I think that everyone knows what it is, but maybe just for the sake of self-engagement of this talk. Let X be embedded inside X cross X diagonally. Having this diagonal embedding, you can have the canonical exact sequence of structure sheaves. So you have all X cross X, X onto all X, and that I, the ideal of this canonical embedding of X. First, from here, you can naturally see that taking the quotient of structure sheaf of X times X and the canonical ideal is going to be giving you the structure sheaf of X itself. So one thing that one can do is, of course, you could ask what is first order neighborhood of X inside here. So you're interested in some sense, tangent, topologically tangent or tangent bundle of X around itself when it is embedded in X cross X. So if I take all X modeled out by ideal square, this is the structure sheaf of first order neighborhood of X in the product of X itself. And of course then, because of this, because I'm modding out literally by ideal square, I can compare structure sheaf of first order neighborhood X to the structure sheaf of X itself. So naturally I can have again another canonical exact sequence, all X cross X, modulo ideal square, projects onto all X cross X modulo I. The kernel of this thing is just I mod ideal square, I mod I square. And I mod I square is the conormal sheaf. So this is conormal sheaf. It's not necessarily bundle. So generally speaking, it's a conormal sheaf of X in its first order neighborhood. Okay. So sometimes notationally, this is called O of 2 times delta, because it's flattening the delta of X in LX cross X of order 2. Okay, so I'm going to use this very easy canonical short exact sequence to construct Atiyah class of X. So let's look at the obvious projection maps from here. Let's call them P1 and P2. So one thing I'm going to do, I'm interested in Atiyah class of sheaves. I'm I'm defining Atiyah class for sheaf. Sheaf. So I'm going to pick some sheaf in here, F, belonging to a median category of OX modules. So let's pick that sheaf. And as you can see, this short exact sequence lives in a median category of sheaves inside here, because these are all OX cross X modules. So one thing I can do is I can, let's call this thing short exact sequence star. I can pull back this coherent sheet and tensor it with the star. Okay, if I do that, because this is projection map onto X, tensoring with the pullback of the F keeps the short exact sequence short exact. So tensor product would be left exact. So you will get F tensored with all of, let's give this thing also a name. So this is also location of O of delta. So O of delta, and then pullback of F, tensored with O of 2 delta, and pullback of F, tensored with I mod I squared. Okay, so then what you can do is you can take this short exact sequence and push it forward down onto X. So you can push forward, apply T1 lower star to this thing, so let's call this thing double star. I'm going to push forward everything onto X. So if I push forward the pullback of F back onto X, because F is an O delta module, it's a sheaf on X. The supported on delta, I will get back F. So this is just F. And well, this one, I'm just gonna leave it as it is. Push forward of pullback of F tensor or delta. And this thing will be F again, but then I need to have push forward the I mod I squared, the low X plus X mod, down on the X, and that's why R short is just the sheaf of differentials on X. This is sheaf of differential of X or delta in my application. Okay, so you get this again canonical short exact sequence. And so from here, you can see that this short exact sequence defines for you a class of extensions of this module by here. So let me write it. So for a sheaf F in OX modules, the short exact sequence A because it's going to induce that here class, I call it A, is called is defining a class of extensions. Is class of extensions, which clearly extensions of that x1 f tensor on the delta, which is called Atiyah class. All that. Of course, this is the name for it, but what does this class of extensions really do? I should tell you what is its geometric really meaning. The Atiyah class, let's call it by this one. So I'm going to call this one Atiyah of F class of such extensions. So Atiyah of F is the only obstruction. In some sense, it's an obstruction class. It's the only obstruction to existence of an algebraic connection on the sheet. Provides an obstruction to existence of an algebraic connection. What does that mean? Is that if this exact sequence is split, then you can see that you will have some algebraic connection on the sheet F. So let's see that. Okay, so note that if I have this here, E2, the morphism E2 inverse provides a homomorphism. Provides the homomorphism of, in some sense, a lift of sections of F to this guy over there. So E2 inverse induces a morphism. If I look at local sections of that, let's say I take some open neighborhood in my variety X, and I look at, I call it U, and I look at U sections of that, then this P2 inverse produces a lift from sections of F on U, sections of P2 of the star of F, or delta, over X times U intersected with the back. So if I have P2 inverse, look at local sections in here, you can lift these sections over here. And where do those sections live on? They live on X cross X, restricted to U, that is X cross U, but then also restricted to the diagonal. So P2 inverse produces a local lift of section.
Sorry, I don't understand what is P2 inverse.
Locally,
Oh.
locally, just the local inverse map in this part.
Oh, okay.
So why is it that Atiyah class is an obstruction to existence of an algebraic connection? Now suppose, if S, let's call something, S is an OX linear splitting of short exact sequence A. So let us assume that the short exact sequence in here is a split. I have many ways of splitting it. Let's say one of the choices of that splitting, I call it S. What I can do is I can lift the local sections of that to here and then use the splitting and map over there. So if I compose S with P2 inverse, then I can map locally F to F tensor X locally. And this is basically the choice of algebraic connection. If you have such a splitting, in this report, if that sequence is split, there's no way possible to lift F to here and then project down. And that's the first one. Exactly like how you define it for vector bundles and so on. Okay, so Atiyah class is the set of non-split extensions, and it provides therefore an obstruction to such connection. So therefore, class of F provides an obstruction to existence of algebraic connection on this respect. So this is how it is defined. Now, I'm not going to restrict myself to coherent sheets. What you can do is you can take any object of derived category class. It could be an optical complex or any object in the derived category and define a Atiyah class for those groups. So generalizations. If I have F, not a coherent sheet, but an object in the bounded derived category X, let's call it F dot. And I can still define a Atiyah class. Atiyah class of F dot is going to be an extension X1, F dot, F dot tensor with or a variety. So that's the first layer generalization you can do. Of course, the sheaf of differentials in some sense understands what to say. So it's definable and well defined for us for the purpose of applications only when X is smooth. So when X is singular, you need to replace this thing. So the second layer of generalization, this is generalization 1, generalization 2. So infinitesimal cotangent neighborhood of X will have many other terms. So it's not going to be sufficing to use just for sheaf of differentials. So we can replace omega of X with the cotangent complex of X. Cotangent of X, which I'm going to denote by L dot of X. Okay, so that's what we're going to use for our purposes. I'm going to work with cotangent complex. So I guess I'm not going to spend much time telling you what the cotangent complex is, mainly because I think everyone knows it, first of all, but then there's plenty of literature on it. Okay, so one thing I can do, all right, so if I have X singular, you can embed X into something smooth, and you see mainly talk a lot about this thing. So you can have some smooth variety or scheme, and then construct somehow the cotangent complex of embedding of X inside something smooth. So you can take a sheaf of differentials away, restrict it to X, and then this is a sheaf sitting in degree 0, and then there will be naturally a map from, so if you have the ideal of this embedding, there is naturally a map from conormal sheaf of this embedding into the restriction of sheaf of differentials away from X. And then there are many other terms. So this cotangent complex keeps going in negative degrees to have it in infinite terms and so on. But we are not interested in working with cotangent complex with infinite terms. We are actually interested only in cohomological truncation of this. So in degree -1, we are going to truncate this thing. So the thing I'm interested in is the truncated cotangent complex. What that means is I'm just going to look at this morphism, and I'm going to replace this term with the kernel of this morphism. So I'm going to cut it. Because that's what for our computation together. So, all right, so that way we can have a generalization where I have the most general object you're interested in, object in the derived category. And this one I replace with truncated cotangent complex. So I'm going to call this universal truncated Atiyah class of F dot, an element with the bounded X, and it is given by an extension again, X1 F dot derived tensor product with truncation of the cotangent complex. This is what you're interested in, and this is an extension group over X. In some sense, it's called universal because it's not going to depend on the choice of embedding of X inside ambient discrete variety. This object, this extension, is defined by Hoiberg's and Thomas. Daniel Hoiberg's and Richard Thomas. And I think it is in a 2010 paper. And the technology of constructing this extension was really fascinating. Provided a lot of later on hints onto how to deal with moduli spaces of sheaves and so on, and was using the Fourier multiplexer. So somehow
Does one need some assumption like the perfect obstruction theory?
I'm going to tell you about that. You don't need an assumption. Yes, but in fact, you're asking the question, which is, you didn't ask me, well, now you did ask me, why do you truncate? The perfect obstruction theory has to do with truncation. So let me actually tell you what is the usefulness of all of this. Before telling you about that, let me just define for you one more thing, which is I'm going to use it. So universal, again, truncated. I'm going to truncation kind of complex. And I'm going to add this other word, relative, at the class of an object. Bounded direct attributes. Let's just say what this is. Let us assume that I have a situation. Here's a scenario I'm going to put up. Let's say I have a situation where I have two projects or two schemes. So I have X and I have Y, and I'm looking at X times Y. And I'm going to call these maps P1 and P2. And over here, let's say I have an object in bounded direct category of X times Y. So over here, I'm just going to replace X with X plus Y, and I can construct truncated, universal truncated vector class of that. So let's just write it down. So I can have universal truncated Atiyah class of F dot going to be an extension over X cross Y, F dot, comma, F dot tensor with truncation in degree -1 of X cross Y, L dot of X cross Y. The reason I want to describe this relative is that now we can see that L dot of X plus Y is in fact pullback of the potential complexes of X and Y. So it's going to be P1 upper star of L dot of X plus P2 upper star L dot of Y. Well, I can just write down without truncation. Wherever you think that I need to add the truncation, do so in your head. Okay. So if I do that, now what I can do is, because this potential complex is the sum of the pullback of the potential complexes, one thing I can do is I can project L dot X plus Y onto one of the factors. So what I can do is I can project this thing onto E2 of the star of L dot of Y. I can do that. So if I do that, then I can see that naturally via this projection, I will get an induced map from X1, F dot, F dot, and L dot. Y to X1, F naught, tensor, pull back of L dot. But because of the way we have constructed this picture, basically L dot of y is the cone of L dot of x plus y when you cone it off the other than L dot of x. So basically, it's like I can embed L dot of x in here. If I take the difference of these two, that's L dot of y. So L dot of y at the same time is in fact potential complex of x plus y embedded into x. So this object that we get over here, if it still lives as an extension group over x plus y, in fact, we could notationally, because of this reasoning, we could call it universal Atiyah class of f dot over x plus y. And this notion of relative Atiyah classes is something we care about. Okay. So what is the reason we are studying this? And now I can get to your question and relations between these deformation obstruction theories. Question is universal class of f dot. Then x, y is of interest. Okay, so let's cook up some scenario. So, example, let y be the n of x gamma be defined as modular space. Modular space of objects derived capital of x with fixed numerical data, which I'm going to just call. So for instance, if you're interested in moduli space of coherent sheets on X, gamma would be the churn factor. Churn factor, a nice moduli space. And then you have X plus n mapping to X and mapping to your moduli space. And let us assume that your moduli space is nice enough, so you have one of these scenarios where you have a fine moduli space and so on. And your moduli space comes equipped with a universal object. So let's say I have in fact some universal object over X plus n. So then I can construct relative universal truncated Atiyah class of this universal object or sheet. Okay. So for the sake of simplicity, assume for now, assume F universal is the universal sheet. But of course, you can extend it to object and graph category. So you're not going to, without loss of generalization. So, okay, so if you have that, then I can just write down universal relative Atiyah class back. So universal relative Atiyah class G x plus n relative x going to be x1 f tilde tensor pullback of potential complex of the moduli space. That's what it is. This is an extension group over x plus n. Now I can actually use an isomorphism between this group. I can write this as an homomorphism in the derived category of x plus n. I think book of any book in derived category has this. Donaldson-Thomas, anyone in the book. We can write this as a morphism in the derived category between f tilde and f tilde tensor with impact of L dot of m shifted by 1. So as groups, these two are equal. So looking at morphisms in drive category and looking at morphisms over a variety are matching together to include this shift in the drive category. Then what you can do is, again, any book in teaching drive category actually tells you that this morphism is the same as homomorphism found the drive category of S plus N. You can basically put this F tilde inside here. So you can put this guy inside here, R hum, over the same category, F tilde F. And then just look at, isolate this piece, basically. This is also something that you can do. It's allowed to do. There's an isomorphism between these two groups. Then you can use variability. By variability, authentic variability, you can actually see that. So authentic variability tells you that if you have this morphism in the drive category upstairs, you can realize this morphism downstairs. Pick where you want to do it. So I'm going to use variability along P2. So I'm going to push everything down onto P2. So what happens is that you can push everything down onto N. So it's going to be a homomorphism. This time in the drive category of N because I'm landing on N. And then R P2 lower star of R hum F tilde F tilde. Cotangent complex, this time the pullback of cotangent complex will be replaced by just the cotangent complex of M. And not of M itself. But you need to pay a price, and authentic variability tells you that you need to twist this contravariant component of this R hum with the dualizing complex associated with the projection map. So this projection map has a relative dualizing complex. Relative dualizing complex. And I'm going to call this relative dualizing complex omega dot of P2. So you need to twist these binaries. That's what they teach us to do. Twist it by omega dot of P2. There's a shift by 1 in here. And as you're doing that, they also tell us that when you twist it, you need to also pay attention to the relative dimension of the fiber along which your projectile goes down. The relative dimension of this minus M is going to be dimension of X. Let's say dimension of X, the variety over complex numbers is D. You need to have a shift by D in here. Okay, so this is what makes this morphism equal to this morphism, isomorphic. Yeah. Okay. So what is the result? Now I can just think of this as a morphism with drive category of the moduli space. I'm going to put all the shifts and so on one side. So this is basically R P2 lower star, R hum, F tilde, comma F tilde, twisted by relative dualizing complex. I'm going to put all the shiftings on one side, so D and then minus 1. And this gets mapped to L dot. Okay. Of course, as I said, I'm working over the truncation. So this is a morphism in the derived category of your moduli space that you will get. Right. Now, if you investigate after investigation, you realize that. Let's give this morphism a name. We're going to call it phi. You realize that H star of phi is an isomorphism. and H minus 1 of V is an epimorph. Suggestion. And this is the very definition of deformation obstruction theory. It's an object in the derived category of the space whose homologies understand tangent information of that space. So H0 of this guy are basically telling the deformations of points that the moduli space parameterized. So H0 of phi being isomorphism tells you that there's essentially no difference between cotangent complex of the moduli space. And then H minus 1 are obstructions to those deformations, and this one has obstructions, naively speaking, bigger than obstruction. So this is called deformation obstruction complex. Let's give this some name, E dot. Because it captures deformation as obstructions, E dot is called deformation obstruction theory or deformation obstruction complex. You asked about perfect deformation obstruction. It's not necessarily perfect. This is perfect or non-perfect deformation obstruction theory. So if you say deformation obstruction theory, it's just saying that it understands deformations and obstructions of the space. That's it. Now, if this object has no more homologies, so if you take over examples, for instance, let's say dimension of X is 3, you have a threefold. This will be R2. If you take R2, you will have X2, so that's obstruction, R0, obstructions, and the other ones will be deformations. If it has no more homologies, then it's a perfect deformation. If it has more homologies, then it's not perfect. In fact, cotangent complex of the moduli space itself is a deformation obstruction theory, but it's absolutely almost always non-perfect. That's why working with it is kind of not really suitable. So, all right, so as you can see, universal Atiyah class of a universal object when you're working with moduli theories is useful because via a sequence of isomorphisms gives you a nice object in the derived category of your moduli space together with nice map that tells you about deformation and obstructions of points parameterized by that moduli space. So let me say a little bit about these deformation obstruction theories. So another thing I would like to emphasize, when you first see these things, people think this is the deformation obstruction theory. It's not. It's this complex together with the cotangent complex. Deformation obstruction theory has no meaning if you just think of the complex, but together with the matrix. So it's an object in derived category with nice homological properties together with the matrix. So here are some facts from the past. So when the dimension of X over complex numbers is 3, Richard Thomas in his thesis showed that E dot provides a perfect deformation obstruction theory when determinant of F is fixed for the case of F being a sheaf, F being sheaves. So he was studying coherent sheaves. So this is a simpler case of objects in derived category. And he was saying, okay, I got to this bit, and I have this nice object, and then I can see that all other homologies other than degree 0 and -1, H1, H2, H3 on the left side, -2, -3, all of those homologies vanish. If I'm looking at the moduli space of coherent sheaves where all my sheaves have fixed determinant. So this is defining for the perfect deformation of subjects.
X is smooth.
X is smooth. X is a smooth. Yeah. Its moduli space is totally not smooth, but itself is smooth. Yeah, otherwise it's really difficult because then your sheaves and so on will have non-finite probably locally free resolutions, and then it's impossible. It's okay. Orbifolds is okay. You kind of think about orbifolds as stacks, and the smooth is stacked, so your sheets are over a smooth stack, quotiented by some group of automorphisms. Yeah, that's fine. Okay, so that's that. One of the results. Then this reason that they define this object, Thomas, in their amazing 2010 paper, actually showed that E dot is a perfect obstruction theory. If the canonical morphism X, let me write it down. Kernel goes to xi f comma f goes to hi of all of x. This composite morphism, canonical composite morphism, vanishes for I in the least given or equal to speed. So what is this thing? If you have a sheaf, if you're looking at I self-extensions of the sheaf with itself, of course there's the trace map you can define. What you can do is you can take sheaves, every sheaf for us is going to have a determinant. You can define the determinant. So you can have a map from here to xi, determinant of f, comma determinant of f. F being a coherent sheaf, its determinant is a line bundle. So these guys cancel each other. And you're just left with hi of O of x. This map is called the trace map. The kernel of this map is the Trace3 extension, basically, by definition. So Trace3 extension, which is notation in xi0, is defined as the kernel of this map. So Donaldson-Thomas showed that if xi, Trace3 xi of f comma f vanishes for all I bigger than or equal to 3, this object will become a perfect deformation obstruction. So here you don't need fixed determinant. This is the advancement that they introduced to the field, meaning you don't need to fix it. Okay, so that's that. Now, the reason I'm telling you all about this is because these are all nice. In the, correct. Yes, this is all in dimension 2. I said that already. Yes, I said dimension 2. Okay, so this is all nice and beautiful, and Donaldson-Thomas theory provided many fruitful things about invariants associated with varieties, smooth varieties. In dimensions 3 and 2, later dimension 2 was worked out by them, and so on. But then, the interesting progress continued when people started thinking about dimension 4. What goes wrong? Or what happens in dimension 4? Look at the fibers of this guy. If I put 3 in here, or for d equal to 3, I have, if I look at the fibers of that object over some point of the modulus is realized by a sheaf, I will have 2 non-vanishing homologies. Actually, I will have more. I will have x0, f comma f, x1, and x2. And I will have also x3. I can't ignore that. Okay. So they showed that in some cases, for instance, when you have Calabi Yau 3, you have same duality. These two guys are going to be isomorphic to each other, and these two guys are also going to be isomorphic to each other. If you have a situation where homomorphisms or automorphisms or sheaves do not jump, you can ignore these constant pieces. This one is going to be the same as that one, so you can ignore it. These are constant. You're not going to cause any trouble. Or for instance, if you are interested in X0 part, please vanish. This is C, and the trace3 hum from C to C is 0. And this one is 0. So they will have indeed only two non-vanishing homologies, and that's good. But for D equal to 4, it's way harder because you have X0, X1, X2, X3, and X4. Even imagining that you are in a situation where X is a Calabi Yau 4, you still have issue. Why? Because let's say this is constant and this is constant, so you can ignore these two things. As you can see, homologies of this guy over points on the moduli space produce for you 3 non-vanishing homologies. And you can't construct from here invariant theory. So this object called virtual fundamental class cannot be constructed here. So virtual fundamental class a priori cannot be constructed. Okay, so there are many recipes that people came up with trying to fix this issue. One of them, well, I think, if I really want to be fair, I think the first people who addressed this issue are Richard Thomas and Donaldson themselves, because there is this nice paper of theirs, gauge theory and complex geometry, something like that, higher gauge theory on complex varieties, in which they were kind of suggesting that one thing one can do is there must be some situations where this guy, this middle term, can be written as a sum of some vector space and some isotropic vector space and tool. So V is an isotropic subspace of X2. They were kind of using language of differential forms and so on. So they were saying this X2 part is the middle cohomology, and kind of they were thinking about self-dual connections and anti-self-dual connections. So they were saying that maybe this X2 is composed of self-dual and anti-self-dual. And then in a situation where the X is Calabi Yau 4, they say, okay, so what we can do is we can think of half of this complex and cut it in half and think of a two-term complex which is composed of one homology which gives you X1 and the other homology giving you half of X2. And if I have Serre duality, this other half is literally just the same because V dual is dual of V and X3 is dual of X1. So if you can have a canonical splitting of middle cohomology like this, then you can, using this Kuronishi theories and so on, using these two cohomologies, you can construct locally virtual cycles. But this was suggested by us. Other people who worked it out, really, in more detail later. So of course, for the sake of, so Donaldson, okay, Donaldson, Thomas, I suggested the idea, Conan Liu and his student Sao worked it out. So they would look at moduli space of vector bundles, which have this property, and then they said, using Kuronishi theory with this two-term complex, locally I can construct virtual cycles. And then they were saying, over the moduli space of vector bundles, hopefully these cycles can glue and give you a virtual cycle. So moduli space over moduli space of vector bundles. And then, well, of course, if you take a vector bundle on a variety and you deform it infinitesimally complex or algebraic structure of that variety, the vector bundle does not remain bundled really in many cases. So this was very restricted. That's why Joyce and his company, Joyce and group in Oxford, started this big movement of derived algebraic geometry. So derived approach, derived AG approach. to construction of virtual fundamental class. So class over moduli space M for Calabi Yau forms. So Joyce and Borisov and so on. So Thomas and O, his postdoc, worked out moduli theories of Calabi Yau form varieties without using derived algebraic geometry technique. And I'm going to tell you another flavor where I'm not going to use any derived algebraic geometry, just algebraic constructions. So here's our scenario. Let Y is smooth projective variety of dimension d minus 1. Okay, call it d minus 1, and let X be a non-compact variety given by total space of canonical bundle of Y, and dimension of X over complex numbers is D. Okay, so for me in my talk, Y is going to be a threefold and X is going to be a fourfold, because I want to approach fourfold theorems. That's the content of my talk. Now let's say I have a moduli space M being the moduli space of sheaves. Okay. I'm really being careful. Space of sheaves, F sheaves on X, but compact is supported ones. X is non-compact, variety of dimension D. Y is compact, and I'm interested in compactly supported sheaves. Compactly supported sheaves on X. Okay. Such that F has scheme theoretic support on compact variety Y. So scheme theoretic support is really way stronger than just set theoretical support. It means that the sheaf F, in some sense, does not deform outside of Y. Like imagine that you have a variety Y and its canonical bundle is negative. So you have this X dimension 1 more than dimension of Y, and you are assuming curves. You're studying curves in Y. Curves, because of having a negative normal bundle inside X, they do not deform. So structure sheaf of those curves are going to be sheaves supported on Y, which have no deformations in direction of canonical fiber. So let's say you have that. So scheme theoretic support on Y implies that for any sheaf F in this moduli space, let's say my sheaves have fixed term character and so on, for any sheaf X, F is going to be equal to I over star of G, where G is an honest OY module, and I is the embedding of Y inside X via the zero section of canonical bundle. So basically, essentially, your sheaves on X are the same as sheaves on Y. Okay, if that's the case, then M of X gamma is literally going to be the same as M of Y gamma, because sheaves on X and sheaves on Y are literally the same. Okay. Even though the moduli space of sheaves are going to be literally equal, looking at them as sheaves as torsion sheaves inside X, these are torsion because support of the sheaves on X is dimension of the support is less than the dimension of the variety. Even though the moduli space are identical, on the same identical moduli space, I can put on two different deformation obstruction complexes. So let's do that. Scared. So okay, X cos M. There is this canonical embedding Y cross M. Y embeds inside X. So Y cross M embeds inside X cross M. And then there is a projection onto M. And there is a projection also onto M. These two are literally the same. And on this side, there is a projection onto projection onto X, projection onto Y, and embedding of Y inside X. So this is a nice exact sequence. And then let's say I can have a universal sheaf on X cross M. Sheaves on X being the same as sheaves on Y, that means even in the level of universal families, F tilde is the same as I over star of G tilde. So nothing surprising, but then now I'm going to construct some deformation obstruction complex. If you remember, it's an object in derived category that captures deformations and obstructions of sheaves with a map of the cotangent complex of the moduli. So one of them, I write it for X, it's going to be R I prime over star, R hum, F tilde. F tilde, answer with omega pi, D minus 1. If you remember, this shift was dimension of your variety minus 1. So D minus 1, D is dimension of X. Together with the map to L dot of M, and we decided to truncate things a little bit. So that's one thing. And then phi of Y, R pi prime over star, R hum, G tilde, omega pi prime. Dimension of Y is D minus 1. So D minus 1 is D minus 2. Again, L dot of M with the truncation. So you see, all I'm doing is my moduli space is the same. If I think of my sheaves as torsion sheaves in the D-dimensional variety, this is the deformation obstruction complex. If I might think of my sheaves as G, same as F, in the D minus 1 dimensional variety, this is the obstruction complex. So you would think that these two complexes are the same, but they are not. They're not even equal. So let's call this one E dot of Y. Let's call this one E dot of X. So are E dot of X and E dot of Y similar? I will show you they are not. And they have very interesting difference. Okay, so what is the difference? What is, yeah, maybe 5-10 minutes. 5 minutes. What is difference between E dot X and E dot Y? So let me do a pointwise analysis and show you how different these two things are. I think this is cool to do. So as you remember in this situation that Y is embedded inside X, any sheaf on X is push forward of a sheaf on Y. Now one thing you can do, you can start from a sheaf on Y, push it forward to X and pull it back. But pull back is not going to be the usual tensor product, the derived pullback. You can pull back, derive pullback, push forward of G. If you do that, you will get a map to G. But interestingly, this is not the only thing you will get. You will get something else. So that something else is you will get G tensor with conormal sheaf of Y inside X, and there's a shift. This is conormal sheaf of Y in X. It's telling you that if you start from a sheaf, push it forward onto X and come back, you will get an exact triangle in the derived category that remembers the sheaf G, also remembers how Y is embedded inside X. This exact sequence is constructed by Bondol and Orlov, exact triangle, I'm sorry. And in the majority of cases, in fact, this exact triangle splits in the derived category. So this middle term is going to be G plus this. Here, for sure, it is splits because X is Y is zero section of a bundle on X, and that exact triangle is splits. So if you do that, so for us, let's call this exact triangle delta E. Delta E splits in derived category of where are we? We are in Y. Okay. Now what I can do is I can apply Artan like G to this exact triangle. So if you bear with me, I will show you quickly. So you will have Artan GG. It starts from here. You will have Artan pull back or push forward with G and G, and you will have oops. And you will have Artan G tensor with the conormal sheaf shifted by 1, okay. I'm almost coming to the main point of my talk. The trick is, again, from any basic book on derived category, there is a jointness property between left drive pullback and right drive push forward. You have Artan GG goes to Artan. This exact triangle is in the bounded derived category of Y. You can again push everything back onto X. So this thing you can just push it onto X. I know what's that. You can write everything in here as so this left drive pullback goes to the other side. Becomes a right push forward. And then you will have Artan G, comma G shifted by -1, tensor with the normal bundle of Y inside X. That's it. And I-level push forward of G is F that we had before. So this is telling you something really cool, which is if you have sheaves which are supported on your original variety Y, if you look at deformations of this sheaf, you realize the sheaf has a torsion sheaf on X. Deformations are decomposed as how they are doing on Y, how they are deforming on Y, plus a piece which contributes to their deformation, which remembers how Y is deforming inside X. So this is an object in the derived category, and I'm calling it discrepancy complex, D dot. Now, if you just do this in families and look at what I have in here, look, same thing. I have Artan FF, I have Artan GG. Looks like they are related to each other by that exact triangle. If you actually do that, you will see that E dot of X is becoming E dot of Y plus discrepancy complex, which is due to realization of Y as a zero section of a bundle on X. Okay, so what is the point? The point is that now, if you take cohomologies, you will see that cohomologically, there are so many terms that this guy has, and there are so many terms that this guy has. So you might even imagine that. Funny thing is that for the same moduli as this, you have constructed two honest maps, which are perfectly nice, that both capture deformation obstructions, yet they are different from one another by something really significant. Who has non-zero homologies. This might have H0 vanishing because this is G minus 1. If the sheet is stable, it goes down and vanishes, but it has definitely H1, H2. The point of our theorem is the following. This is a theorem Diaconscu and Yau, that, as I mentioned to you, the deformation obstruction complex is not just an object in the drive family, but it's together with the maps to the cotangent complex. And the way you get the map is, the recipe is, you start from Atiyah classes. So you really need to say, I have sheaves F, construct Atiyah class of sheaves F on X cross M, construct Atiyah class of sheaves G, and they are the same as that, on Y cross M, compare them together. If you do that, and you follow their modularities, you will see that you will get a map from here to here, L dot of M, and you will get a map from here to here. And now you would like to know, this is what we call field X, and this is what we call field Y. This guy produces for you a virtual cycle. Actually, this is Atiyah class. This is found from Atiyah class. This one is Atiyah class of F's. And this guy gives you Atiyah class of G's. And you would like to see whether this map can factor through this discrepancy. So via some heavy analysis, if you look at our paper, you will see that we proved it doesn't. So, point is, there are many moduli theories where you are studying torsion sheaves on Calabi Yau varieties. So in situations where your sheaves can be scheme theoretically supported on X, you can construct a virtual theory of Calabi Yau 4 variety where moduli is virtual fundamental class of moduli space on the Calabi Yau 4 variety can become in fact equal to virtual moduli, virtual fundamental class of the same sheaves on the threefold, which sits inside that Calabi Yau 4 variety. This is a reduction of virtual fundamental class. And therefore, you can actually show that in many cases, Donaldson-Thomas invariants of a Calabi Yau 4 variety with fixed Truncated can become equal to Donaldson-Thomas invariants of a threefold that sits inside there with the same Truncated. This is our virtual reduction. Maybe 10 seconds. This has some nice applications. There is interesting theories which are induced by gauge theory. One of them is called Kappa-Witten theory. Kappa-Witten. It's about sheaves which are supported on some noncompact fourfold, which is given by total space of cotangent bundle of an algebraic surface, cotangent bundle of a surface. So it would be interesting if one can calculate invariants of Kappa-Witten and Witten. Kappa-Witten and Witten look at certain moduli spaces, differential equations, which are optimizing certain Lagrangian action integral over moduli space of certain mechanical system. And then you would like to count the solutions, and those are your invariants, and those would be Kappa-Witten invariants. But if you want to do that, you need to go from a surface to a potential bundle of surface, which is a fourfold. Turns out that your sheets are torsion, supported on the actual algebraic surface. So maybe you can use this technology. The way you can use it is that we degenerate the cotangent bundle of the surface into sum of line bundles. Cotangent bundle, if you look at papers of Yau, for instance, in 92, he proves that cotangent bundle of majority of surfaces is a stable bundle. What you can do is you can degenerate this thing into a sum of two line bundles, one of them being negative bundle, one of them is being numerically positive bundle. So as a rank 2 bundle, this thing is unstable. And then via the degeneration, your marginalized space is pushed to the special fiber of that degeneration. And this is the realm which our theory works out. Because surface, the smooth projective algebraic surface. Yes. So then, if this is your surface, essentially you can look at total space of the positive bundle that sits inside the total space of the rank 2 bundle with a negative blind bundle. And that's a situation where your sheets are really supported on the threefold, but they cannot have thickenings into the fourfold. So you can say, if I degenerate my marginalized space, then essentially I can go to the special fiber of the family and capture invariance of fourfold via invariance of threefold. And maybe that's good to do. I stop here.